Okay, so from previous class we know, in order to estimate or understand the entropy production rate per volume in your flow process or in your kinetics process, so we need to know the flux and the corresponding driving forces exist in your system. Let's take an example, some examples following. If we have a heat flow process, then as long as you know the heat flux times the driving force, then divided by T, so you can get the entropy production rate. And regarding to the heat flux, you can get that from what? From as long as you know the thermal conductivity and times the minus temperature gradient, so you can successfully estimate the entropy or calculate the entropy production rate per volume in the flow process. So the same idea can be performed in the diffusion process, or we call the mass transport process. As long as we know the atomic flux by using this fixed first law is a minus mobility times the concentration times the chemical potential gradient, then we also times the driving force here is a minus chemical potential gradient. Then as long as you get this one, then you divide it by T, so you also can calculate the entropy production rate per volume. Okay, so this is a case when you only so when we have we know there are some driving forces apply on your interesting materials, but don't forget we show you the this equation before, right? And in this part, we haven't have chance to explain more about this coefficient L alpha beta. And as you know, the beta can be alpha, right? So here actually we have L alpha alpha and we have L alpha beta. This term actually we call the coefficient. And how to get from here to here actually is the most important part is the flux, the intensity of flux J alpha will be the linear can be have a linear approximation with the driving force applied on the system. So we got a summation L alpha beta times the F beta. So as you know here beta can be alpha and also can be a beta. So here don't forget we give you an example here actually will be equals to L alpha alpha F alpha plus F L alpha beta times F beta, right? So this we call the flux force relationship or equations. But now in this slide, we are going to demonstrate or explain more about this coefficient. What is this coefficient? Means, or what is the physical meaning of these coefficients? So as you know, we have we take a heat flux as an example. Based on this, you know, F, heat flux of driving forces. We got the many driving forces, possible driving forces apply on our system, right? And this driving force will contribute the heat flux, as you know, in these cases. So in order to formulate the heat flux, we can directly write down like this and have this approximation. And here, what we have is we have each driving force times the partial heat flux, partial with F capital Q and times capital Q, and we plus the partial heat flux partial with F small q times F small q, and so on. But how we can get this equation directly? So this is actually based on we take this heat flux into the take this into the Taylor series. or Taylor series or Taylor expansion near the equilibrium point. The near equilibrium point means the driving force very near to zero, just tiny or very small away from zero. So we can, based on this, we can write it down, right? The heat flux of F capital Q can be write down is equals to this one, and as we know, F0 actually is when the driving force equals to zero, so we don't have the flux here. So now we can, if we only concern one driving force F capital Q, which is a temperature gradient part, and we can write down the J heat flux equals to J capital Q prime at F0 times the F capital Q. So FQ prime actually here is what? Is the means the partial JQ partial with F capital Q, right? And now you times the F capital Q here. So if we have several driving force apply on the system, so we need to sum them up. So that will become, so the expression of heat flux can be expressed like this. Now we have this equation, right? Relationship between the heat flux and various forms of driving force, and we also have the flux and force relationship we learned and show you before, right? So now we compare these two equations, then we will have some idea about these coefficients. This coefficient will be equals to, for example, like in this case, if you compare this one, you find that, oh, actually, this is the coefficient, right? This is L capital Q, and the second term is L capital Q small q, right? Because, for example, if the beta equals to capital Q, so we got the first term will be L capital Q, F capital Q, right? So be this term. So we will say L capital Q, this direct coefficient is a partial heat flux with respect to F capital Q. This is what we call a direct coefficient. And if the beta equals to small q, then the second term will be L capital Q small q times F small q, will be this term, right? So this part will be the L capital Q small q. This is what we call a coupling coefficient. Because these two terms difference, so we call a coupling, which means the electrical field or electrical potential gradient, this driving force contribute on heat flux. So this is L capital Q small q means, right? Okay, so let's explain more about this term and this term. So what's the physical meaning for this L capital Q, this direct coefficient? Is when we apply a unit driving force F capital Q, the change in heat flux, we call it as L capital Q. This is a physical meaning of this L capital Q, this direct coefficient. The same idea can be applied on the direct coupling coefficient L capital Q small q. Based on this, you know, when we apply a unit driving force F small q, which is the electrical potential gradient part, right? And the change in heat flux, we call it is L capital Q small q, a coupling coefficient. And as I mentioned before, when you write down the coefficient part, the right-handed side this term means the driving force, and left-handed side part we call contribute on what kind of flux. Can be the heat flux, electrical current density, or the atomic flux. Okay, so now we know the physical meaning of this direct and coupling coefficient. And some people probably will think about, oh, Professor, when I apply a unit driving force of F capital Q and the change in heat flux, this turns out can be explained like this. When I apply a same temperature gradient or temperature gradient on different materials, the change in heat flux would be what, right? And as you know, if I apply the same temperature gradient if I apply on different materials, the change in heat flux definitely different, right? So, and the same idea, if I apply the same electrical potential gradient on different materials, the change in heat flux definitely different, right? So now we know this coefficient actually is related with intrinsic material properties, right? And the intrinsic material property or transport coefficients or transport properties of materials can be like diffusivity, thermoconductivity, and electrical conductivity. So now you know this coefficient actually is highly related with intrinsic material property, especially the transport material property. Okay, and this part just remind you, as long as there are two driving forces coexist on your materials, you need to know how to write down the heat flux and the current density. Okay, so based on previous slide, we know direct coupling coefficient is highly related with materials property, especially transport. The material property related with the transport resistance, right? And as you know, every material has its own direct coupling coefficient because every material have its own material properties, right? So now we are going to point out or show you these four material properties, how these four material properties related with the direct coupling coefficient. And the first two examples, we are going to explain the first two. The first one will be the thermoconductivity kappa, and the second one will be the electrical conductivity low. And as you know, this is a result. We just directly show you the thermoconductivity is proportion to the L capital Q, this direct coefficient. And the low, actually, electrical conductivity is directly equal to the L small q. But in order to show you these are correct, so how to derive this relationship? So we are going to move to following slides. The first case we want to show you is related with the heat transport part. So the question one here, and the purpose here is going to explain the relationship between the thermoconductivity and the direct coefficient. So the question one here is, what is the heat transport in a conductor with a temperature gradient? So the heat transport usually means the kappa. So now you have a conductor materials, and it is conductive materials. And now we apply a temperature gradient on it. So how many driving forces exist to apply on these materials? Just one, right? So based on this flux and driving force part and only one driving force, so I believe you can directly write down the flux will be the heat flux, so it will be J capital Q, and will be equals to L capital Q times the driving force for the temperature gradient with minus temperature gradient divided by T, because only one driving force. So we can directly write this down, right? And as you know, there's a Forest law, right? So Forest law tell you the heat flux also equals to minus thermoconductivity times temperature gradient. So when we compare these two sentences, we find that the thermoconductivity equals to what? L capital Q divided by T, right? So in your experiments, in order to understand the thermal conductivity of your materials or you develop new materials, usually people will measure the heat flux directly divided by the minus temperature gradient, so you can get the thermal conductivity of your materials. Okay, so this is how we get the thermal conductivity of your develop your interesting materials. Okay, so let's move to question B. This question B is, why is the heat transport in a conductor the same with the A, right? But with the temperature gradient in case of open circuit. Okay, so now the circuit is open. We also have a temperature gradient. And in case of an open circuit, so definitely, probably you will think about what's the open circuit here. Open circuit means actually you connect this conductor with a wire, and that allow that wire to make a circuit. So you can consider, for example, like you can consider that can be connect these conductive materials to the voltmeter. And as you know, the voltmeter actually with a very large resistance, right? So because you okay, so probably you will do this one, right? Use that, and you use, okay, consider this is a voltmeter. Okay, so there's a very large resistance inside the voltmeter, so the current density can becomes approach to 0. But actually that's not that is not so in this case actually the material is suffer two driving forces. The first one is temperature gradient, and because this is a mega circuit, electrical circuit, so probably there's a electrical field applied on these materials. So we got two driving forces. So based on this, you can formulate the heat flux. The rate equals to this, right? Direct driven by F capital Q and indirect driven by electrical potential gradient. And also this term actually Forest law always correct, so will be write down equals to minus thermal conductivity prime times the temperature gradient. And some people probably will ask about, Professor, let's say we just directly connect to voltmeter. Are there definitely there's a driving for electrical potential gradient apply on these materials? I would say probably yes. The first thing is because you make it a circuit, so you also apply a temperature gradient, right? So if this material is thermoelectrical materials, which means when you apply a temperature gradient on this material, they will generate the electrical potential gradient. In this case, then there's a electrical potential gradient apply on these materials. So that can be possible because you already use the electrical wire to make it as an electrical circuit. So this is possible. Okay, so let's move back to here. So now we know we use the kappa prime here because I want to make a difference between kappa and kappa prime. Okay, so the other point is less of two driving forces, so I believe you can write down the current density directly driven by F small q times L small q plus F capital Q times the coupling coefficient L small q capital Q. And as you know, based on this open circuit, connect to the voltmeter because the resistance is very large, so the current can be equals to 0. So here we can substitute F small q, we can just move this term to the move this term to the right-handed side and get the F small q expressed like this as a function of F capital Q, right? And as you know, F small q equals to minus electrical potential gradient, right? So now what we do next, we are going to, this is F small q, right? Substitute this small q here with this one and take the same part F capital Q out. So we rewrite the heat flux can be expressed like this. And we substitute F small q with this term and take the F capital Q out. Then as you know, F capital Q is a minus temperature gradient divided by T. So we move the temperature part inside, then what we get is we get this term, and also this term actually equals to minus kappa prime temperature gradient. So compared to these two parts, we know this term is the kappa prime. Now you know this term actually is kappa prime. So what is a kappa prime means? Kappa prime actually, if you look carefully, you find that L capital Q divided by T actually is kappa. So kappa prime actually equals to kappa minus the extra term. And this term actually, this is positive, and positive. So all this term actually is a positive. So kappa prime must smaller than kappa because you minus a positive term, right? So now we know what we know in this case. If there's two driving force exist on your materials, and in this case you want to measure the kappa, you want to measure the thermal conductivity, you are going to underestimate the thermal conductivity of your materials because you are going to measure the kappa prime, right? Why? In this case, how do you get the thermal conductivity? You will perform the same idea with that you perform on A, right? You will measure the heat flux divided by minus temperature gradient, then you got the value, and you probably will think that is the thermal conductivity of your materials. But one thing is missing. One important thing is missing is the kappa prime, or the value you measure. You think that is a thermal conductivity. Actually, it is not. The reason for that is there's the other driving force, electrical field, exists on your this system. So the kappa prime you measure actually is not exactly the kappa of your materials. They minus the extra term. Okay. So here the first things we know, we successfully link the direct coefficient L capital Q with our material property, thermal conductivity. And the second important part is that we know that as long as you perform the thermal conductivity measurement, please do that under the no electrical field exists on your systems. Otherwise, the kappa prime, the thermal conductivity you measure, you are going to underestimate the thermal conductivity of your materials. Okay? And probably some people will ask, Professor, how about if the heat transport in contact with the temperature gradient and also the concentration gradient? And how about in that case, the thermal conductivity kappa prime I measure will be also underestimate? Or is that the incorrect thermal conductivity I measure of my materials? So in that case, there's still two driving forces coexist on your system, right? So the kappa prime you measure actually is not the real thermal conductivity of your materials. The same idea. Okay. So next, we are going to move to the other example. Here will be the question 2. And what we have is we have a metal, and we connect it to a battery. Battery means we apply the electrical field on these materials, on these metals. And what would be the expression of J, current density and heat flux? So based on this flux force equations, I believe you can very quickly write them down. And the question here is describe how the apparent electrical conductivity law of a conductor changes in isothermal and or adiabatic conditions. So he asks you about apparent electrical conductivity. Apparent means the electrical conductivity you measured in your systems. So the first question A is isothermal conditions. So now what's the isothermal? Means we don't have a temperature gradient. So which means we don't have the F capital Q. It equals to 0, right? So we don't have the driving force for heat flux. So when you try to write down the heat flux and the current density expressed like this based on the flux force relationship, and we know the temperature gradient equals to 0, so we got this one, right? We can write down the heat flux equals to as a function of minus chemical electrical potential gradient, and the current density also is a function of minus electrical potential gradient. Okay, so don't forget there's a very important law we call the Ohm's law. Ohm's law tells you the current density equals to minus electrical conductivity times the electrical potential gradient. So based on this relationship, we've confirmed that the electrical conductivity law equals to L small q, this direct coefficient. Okay? And the B actually question will be under the adiabatic condition. So what's the adiabatic conditions you learn in thermodynamics? It tells you the heat flux equals to 0, right? So heat flux equals to 0. So the purpose here is we are going to use the Ohm's law to get the apparent electrical conductivity. So this term is more important because we are going to write down equals to minus low prong electrical conductivity or electrical potential gradient. But this term, temperature term, is bothering us, right? We need to substitute this as a function of minus electrical potential gradient. So based on this, we use this rule. JQ equals to 0, so we can make this relationship. We substitute the minus temperature gradient divided by T part as a function of electrical potential gradient. Substitute into this one. So we take the minus electrical potential gradient part out, then equals to minus low prong electrical potential gradient. So the inside part actually is a low prong is a electrical conductivity we measured in our system. How to measure that? As long as you measure, you measure the current density, you divide it by the minus electrical potential gradient, then you will get the value, right? That will be a low prong. And here you also know that under the adiabatic conditions, the low prong you measure is not exactly the low, right? This is a low, right? Actually, it's a low minus the positive term. So here we know what we know. Low prong equals to low minus extra term. So let's also tell you in order to have or measure the correct or accurate electrical conductivity of your materials, you must perform all these measurements under the isothermal conditions. Otherwise, you are in most of cases you are going to underestimate the electrical conductivity of your materials. Okay. Today we ended here.